trên máy bay, đường máy bay đi đến Đà Nẵng thì hy vọng là sẽ gặp nhóm học viên Đà Nẵng trong cái buổi thực tập, hoặc là khi mà Thiện thăm viếng Đại học Bách khoa. Thì tiếc là Thiện không có đến được để mà tham dự trong cái lớp này ở ngày hôm nay, nhưng mà hy vọng sẽ gặp được tất cả những học viên ở Đà Nẵng. Thì để bắt đầu thì tôi chắc là phải chia sẻ cái này trước. Tôi sẽ chia sẻ cái kết quả của cái pre-assessment. Thì cảm ơn tất cả mọi người đã đưa ra rất là ngắn, rất là gấp, nhưng mà cảm ơn mọi người đã trả lời đầy đủ. Thì bây giờ là có 25 câu trả lời, 25 câu trả lời, và điểm thì cũng cũng như bình thường, có rất nhiều điểm rất là giỏi. 100 là tối đa, thì có một số điểm thì 30 đến 60. Nhưng mà một lần nữa, đây là chỉ là pre-assessment, chỉ đọc qua sơ sơ chứ chưa hiểu gì để mà biết, biết là những cái khả năng, những cái kiến thức đã có sẵn thôi. Và bây giờ thì tôi không có sẽ có yêu cầu lúc trước là cho đi qua những cái câu hỏi này, nhưng mà tôi bắt đầu bằng cái lecture trước, khi mà mọi người còn khỏe, rồi sau đó là xong lecture rồi thì mình có thể là lựa chọn đi vào trả lời những cái câu hỏi này, hoặc là nói chuyện về labs. Thì hôm nay, đề tài hôm nay là là power planning. So we had planned earlier to do power planning next week, on Friday. But due to the complexity of it, and due to the labs already ahead, so I decided to cover power planning today. Therefore, the materials, I have to prepare. We prepare week by week now, because we rush to start this class in time for the semester. So we didn't have enough time to prepare the entire class, and we prepare the lectures as we go along. So I apologize for having sent these lectures sometimes late, because we are trying to provide as much information as we can, but a lot of these things are created freshly before class. So I appreciate your patience on this. So now we're going to talk about floor planning. So as an outline, we have gone through several steps in planning, and we have the chip size defined, I/O cells placed, macros placed, and today we're going to talk about standard cell placement areas and power grid. So since we already the standard cell placement is meant to be going into deeper details about the placement rows and different things related to placement areas of the standard cells. But as we look into power grid, we think it's more useful to go over the power grid, and the standard cell placement. Hopefully people can read. So I decided to jump into power grid. Let's see the. So let's talk about power grid creation, or sometimes you see as power planning. So the purpose of power planning is it is a very, very important step in floor planning. So it involves, first of all, analyzing the power consumption of the chip, and based on the power consumption, we'll know what we can do, should do, to distribute the power from the I/O areas to other cells in the core areas. You guys see my cursor, right? Dave, Lou.
Yeah, we can see.
Okay, yeah. All right. So the purpose is providing power to our cells, right? And because the cells are the standard cells, the macros, they are like robots. They need power before they can move around. Without power, they cannot do anything. So we need to route the power from the pad. The power comes from the outside. Sometimes if you have a PLL on-chip phase lock loop that generate the clocks and the power that generate the I got mixed up. On-chip regulator, then the power can come from on chip. So the one of the purposes is to minimize IR drops. So you see why IR drop minimization is something that we need to pay attention to. Give me a minute. Sorry, I have to close the door. So you need to minimize IR drop. There are maximum IR drop constraints that due to the time enclosure constraints that we'll learn a little bit why we need to be concerned about IR drops. And then we need to minimize a self-heating for EM purposes. We'll see what they are about. And then last but not least, we want to be accurate. By being accurate, then we can avoid over-designing of the power grid. So if we do too much over design, then you will take away the routing resources, and also you will make the chip bigger, and so therefore more expensive. So you want to be you want to avoid over designing, right? So the power grid, how it is created and analyzed, a lot of things depend on the power consumption. So this is just a little bit review of what power means in electronic circuits, VLSI. So let's see. So this is a review. So as you know, right, power is current times voltage, right? And the if there's a resistor, then power dissipation, power consumption is I times S squared times R. The power is equal to V squared over R. So it's I squared R. So this is power dissipation through a resistor. And the energy that is needed to charge a capacitor is in integration of I VT dt. Or C dVdt VT dt. And then after you take the integration over the voltage charge on, you need to charge a VC on the capacitor. Then the charge stored here is equal to 1/2 of the C, which is the capacitor here, times the square of the that you charge up. So that's the basic power. And then there's a little detail about the charging of a capacitor. So if you have an inverter here, you have an output load. So energy stored in a capacitor, like we mentioned over there, is 1/2 of a C load times VDD square, because you charging on your circuit, VDD is charged, VL becomes VDD. So that's the energy stored here. But energy drawn from the power supply is something else as well. So as you go through the equations, and you will see CL times VDD square. So it's twice as much. So because half of the energy is dissipated, through this PMOS, right? So the other half is stored here. So likewise, if you discharge the CL when V out goes from 1 to 0, then you go through the AND transistor. So the energy is dumped into ground. So half of CL VDD square is dumped, and half of it is dissipated in this AND transistor as heat. These are dissipation as heat. Okay. Um, so these energy affects battery, but you learn later on. Okay, so the sources for power dissipation are the total of a power is a dynamic plus static. So for dynamic, you have switching and short circuit. So we can go over this a little bit later. I hope I have pictures. But the switching is when you have this operation, when you go from V in going from 1 to 0, you're charging this capacitor, and V out it goes from 0 to 1. You're switching. So that's a switching current. But as V in goes up, um, um, I cannot draw because I'm zooming in, but if V in goes up and it slowly going up, then when V in passes the threshold of these two, then there's short circuit current that go from VDD to ground. That part is part of the dynamic power when you switch. But the static power is really there is a consumption when there's no activities, no operations on the circuit. So it involves VDD times the current, the substrate current, the gate current, the gate that goes through current. If you look at the three the cross section, then the substrate will have some current. The gate will have some current through the gate oxide. The junction, the N plus and P plus have leakages on that junction. And there's something called contention, meaning that if you have two gates driving one load and they are fighting, so there are overlaps of signals that create some contention that will consume some power too. So those are added up into static power. Just some review, and then
Thank you.
switching.
May I add a comment?
Yeah.
Yes, I want to go back to the leakage current, and this is very important in circuit design. That
Yeah.
the leakage current is proportional. Well, actually, proportional with the temperature. So when the temperature increase or at a higher temperature, the leakage current is goes up very high, especially for the latest and greater technology node, like 22 nanometer, 10 nanometer, 5 nanometer. The leakage current is very high, and sometimes we had a leakage current at a high temperature, even higher than dynamic current. So when we design, we
Yeah.
have to take that into account, especially for the chip that target like automotive or industrial, which had to work at like 125 C junction temperature. The leakage current very high. So make sure that our circuits or our power grid had to account for that power voltage at the high temperature.
Yeah, very good point. So thank you, Vu. So I want to add to that, right? So leakage power is the most important thing in wireless. If you have iPhone, you have a cellular phone. This is the guy that drain your current, drain your battery. So the challenge in designing SoC for cellular phone application, wireless application is not speed, but is static power. And as you go lower and lower, more advanced technologies, the leakage you become exponentially higher, and managing leakage is very difficult. And on the temperature side, there's something called temperature inversion, where at minus 40 degrees, you have more leakage current than the high temp. So there's a lot of things. As we go more advanced in IC design, leakage current is one of the things that we have to worry about a lot and do optimization for. Yeah, thank you, Vu. So now on switching power, right? Switching power. So this is this example of a circuit that we can take a look to understand switching power. So you say switching power is 1/t, the integral of IDD VDD dt. Right? So but as you can see in a circuit that you have a switching frequency, that becomes CVDD square of the switching frequency. What it says is that the switching power is increases when you increases operating speed. So that's something that that's a review. And short circuit current, like I said, there's an inverter here. If there's a P and an trees, when you have a slow rise and fall time, then the time that is in between there are short circuit current flow from N to P. So usually it's about less than 10% of the dynamic power. And we don't pay attention to them, but sometimes, sharpening of the inputs will help with the power, even though it will increase the other part of the dynamic power, but something we don't have to worry about now. So, and the static power is really related to, over here, we already mentioned it, right? So it's consumed when the chip is in quiet mode, nothing happening, just only leakages, but no, so all the power, all the devices are off, but it's just leaking, right? So that's a quick review, actually. So that's a quick review of power. So we're not going to visit those things until later on when we try to analyze the power grid for different electrical behavior. But we're going to go through this to understand how we build a power grid without worrying too much about power and voltages and everything else. Just some layout thing here. So creating the power structure is called power distribution structure. So you pretty much have the power from the pads, and you want to distribute the power to the standard cells to the macros. So what do you do? And sometimes as a note, for simplicity, you're not going to see more than one voltage in the core in all the test cases that you are playing in the lab, but in reality, for SOC, you have multiple VDDs and multiple grounds, sometimes in the chip. So just a note there. So in this case, we only have just one for the core. We call them VDD VSS. Sometimes they call VDD core VCC, whatever. But in our documents, we call them VDD and VSS. Without anything, we mean the core voltages. But there are also VDD and VSS on the IOs. As you know, the IOs have different voltages, and they're very strong, noisy, and very they can interfere with a lot of stuff if we're not careful. So you have on here like one VDD-IO and one VDD core, and you have VSS and IO and VSS core. So you want to create. So the step in creating the power distribution structure is that you create the power and ground net. So in synthesis, you don't have those nets in the net list, but in the physical world, you need to have a net for VD, a net for ground, for the core. So you create the net in the logical view, and then you connect them in the physical view, right? And so in the physical, you have two types. Basically, one is called rings. So ring is something that enclosed like a closed loop here. So as a ring, either from the core, you remember this. There's an I/O area, and then there's a core area that encompasses everything other than the I/O paths. And then the macros in here. So the rings either around the core area or around a macro, or all the macros. And then you have what we call straps. Straps are, lines that are either vertical or horizontal that sometimes you call them stripes. So you use those thick straps to distribute power to the standard cells. We'll go into more details on that, but basically that is a creation of the power distribution structure, and exactly how we do it, we'll go over it a little bit more detail. So first of all, power net connection. Power net connections, like I said, is not in the synthesized net list. So we create a net, and then we need to have a logical net in order to do any operations. So now and then you will create. You want to create. You want to connect them. But first of all, let's go through some terminology. So in here, assuming that you have VDDs and VSS going from off chip, so you have we call paths, right? So just terminology. So all these VDDs, red are VDD paths. And then VSS in green, in blue, they call VSS paths. Those are paths. And then you have rings, right? The ring is around the core. This is a core ring because the core area is in here. And then you have standard cells. These VDD VSS, you call them pins, right? The paths here and the pins here and the rings here. And then you have a memory or macro. Typically, you either have straps like this as VDD and VSS pin, or sometimes you have in your lab, you will see you have rings inside already of VDD and VSS, so people can connect the power to the ring, and then internally they will distribute the power. So these are called pins as well. And then you create a code, you connect them using maybe these animations of order. And then you have nets. So we create a VDD net and we create a VSS net. When you create in logical, you don't have this physical anymore, and then you run some command to route them, then you have physical. Okay. And then right over here, so you can connect the VDDs and VSS pins of the memories to the net. Therefore, you connect to the ring, or you create the ring and you connect them to the net. Therefore, you connect them to the path. They are when they are on the same logical net, the router will connect them automatically. You just need to define them. So this, like I said, sometimes you will route over top of the memories and veer down on these internal power grids, or sometimes you just route to the a ring. So you connect logical nets by connect global, uses this command connect global net. This specific to Cadence tool. And oops, sorry.
Until before you move on, may I ask a
Yeah.
question? Yes,
Yeah.
I think it's helpful for the student.
Yeah.
Will you explain why the power and ground paths were placed where they are?
Okay. Yeah, this is the the perfect example of you have power and ground everywhere, right? But sometimes you don't have the luxury to have more than a pair, for example. But you're talking about the past, right, Vu?
Yes, the path, the
Yeah,
number of paths, but the number
yeah.
of power and ground paths and their location
Right. So that
in the
location,
pathway.
so yeah, so it has a lot of thing to do with the best location for IR drops. Maybe we'll have some other additional information, and maybe related to board that I don't know. But but ideally, the things that is in question here, it will be the IR drop. As you know, we will have to minimize the IR drop. So if you have here the location, the distance between this and any internal places in the on the chip, you have you are close to either of these pairs of paths. Maybe it has something to do with also the board design. Will you want to add to it?
No, that is the point that important. That is the I drop that you distribute them, spread them out. So anywhere in the logic that any cell can also get and draw the power, and get from as close to the source as possible. The source here mean the power supply pad or pin.
Yeah. So the closer you are to the path, the small IR drop. If you have small IR drop, you can tell it's better for your speed and sometimes power as well. So okay, that's good. And in addition to the standard cells, right, you need to connect and to standard cell and macro power and ground. You also connect something called tie cell. Tie cell is something that you need to understand because it's an important part of the physical design. So tie cells are the cells that we use to represent a constant zero, a constant one, right? So as you know, in digital circuit, constant one is a VDD. So if you have a gate inverter and you want to tie that gate to one or zero in your logic, right? You would normally just connect them to VDD or to ground. But the problem is that the input, there's a gate here. The gate oxide is very thin. Any voltage surge on the gate oxide can damage the gate oxide. So that's two things that can happen during friction due to antenna effect that you will need to learn later. There will be voltage surge when you put down the last layer of metal on your chip, and the voltage surge, if it will go directly to this gate, it will rupture the gate. So we don't put tie this one to VD directly. We use a tie cell instead. The tie cells are created in such a way. This is a tie high, means that if you always need to be one, it will be connected something called we call it diode connected, where VD and VG are connected together. So VD connects to VG connected together. As you remember the transistor theory, that VDS equals to VGS. Over here, VDS equal to VGS. So therefore, VDS is higher than VGS minus VT. If you look at the transfer curve, that means that the transistor here is in saturation. So that means that this guy, when you look at here, then this node always at zero. So if this is always at zero, then it will turn this gate on always on. So out is always at VDD. So out is still one like this. But now the VDD is touching not the gate, but touching the diffusion here. So the diffusion here is much more is better. It won't be rupture. It have breakdown voltages and everything, but it's a lot higher than the gate. So this is how you do it. Likewise on the tie low is just a reverse. So the P here that put a 1 here all the time. So this one always a 0. So that's something to understand. So in the net in the gate netlist coming in from synthesis, you only have 0 and 1s. You don't have tie cells, and then you will, in the physical world, you will insert them, and it's automated, but you have to specify them. And feel free to interrupt me with questions. I love questions. Please raise your hand or type questions, and Boo and Dave and Bud can tell me. But I would prefer to have questions during this. Yeah. Oops. Keep on hitting
So
the
Phil,
wrong
we
one.
did have one question come in. Does
Yeah.
does using tie cells cause any bad effect on the circuits?
Tie cell bad effect on the circuit? No, absolutely not. You would imagine that, yeah, it is inserted and it sits there and doesn't do anything, right? So because this is a constant, so there's no timing going through it. So I sit there and just do that. It has no. I'm not aware of any negative effect on it. Does Bud and Boo, do you guys know if there's any negative effect on it?
No, then it took up some space, right?
Yes.
Okay, yeah. So it's a must. If you don't have it, your your chip will not be yeah.
Yeah, I mean
reliable.
the tie cells is very important. Starting at about 130 nanometer design below. At a bigger geometry not a must, but at 130 below, you gotta have it.
Yeah. Okay, so
And Phil, the next question to come in is the inverter could have input logic 1 or 0. So how do we determine which tie cells we need to connect to inverter?
okay, yeah, thank you. So it is logic, right? So so when you, but it just comes, so your logic, right? Your logic design calls for a 0 or 1, right? So it's just already predetermined, because sometimes you want, due to digital logic, sometimes you don't, you have to have a 1 or a 0 on a particular gate, because you want to drive it, you want to control that. So yeah, that's the answer is coming from the input netlist. Okay, and so that's power net connection. So now, how do you build the different things, starting with a ring, right? So a ring, like I said, 2 rings, core rings and macro rings, right? Or block rings. So they call block. A block really is just a macro or custom cell. They call it just a block, meaning a cell, but bigger than standard cell. We call it a block. So you use a command add rings, right? To do that, and you, before you put a command add ring, you want to tell what kind of ring you're adding. By the way, thank you for the questions, right? So no question is you ask question doesn't mean you don't know. You ask question. Don't worry about asking stupid questions or asking trivial questions. Yeah. Okay. Which case of VD of IO path is lower than the core VDD? Good question. This is really this is so typically is higher, because you can see, internally you have low voltages, right? Because you want to be as as low power as possible, but sometimes you need more VDD to meet the speed. But the outside is a physical world, right? So physical world usually it require because of the sheer size of the board, whatever it needs to drive. Usually the IOs are higher voltages on the outside of a typical SoC. For specific SoC, maybe some analog SoC or anything like that. I don't know. It's possible that I haven't worked on any IC that have lower I/O voltages. But there are in the past there are some TTL logic that was 0.8 volt, right? So you interface to the very old TTL logic. By the time maybe you have to be your IOs are higher lower than your internal voltage, maybe that by the time 1.5 volt whatever, but in modern ones I haven't seen it. Yeah, good question.
So if I can add a comment there, and few. So
Yeah.
the question is, in which case the VDD of the IO pad is lower than the VDD core. So today, like for 22 nanometer or lower, the typical operating voltage is between 0.5 to maybe 0.9 volt. And for the iPad, in the past, the iPad was like 1.8, 3.3, 2.5 volt. Now it moving down to 1.8 volt. That's a typical LV-CMOS iPad. But for the iPad, a special interface like DDR for the interface to external DRAM, because this iPad can operate at very high frequency, like 2.4 gigahertz or higher. So the voltage have a significant contribution to the overall power consumption of the IO pad, and so the power consumption of the system. So the new type IO pad like LPDDR4X, LPDDR4 is 1.1 volt nominal, but LPDDR4X is 0.6. So that is one of the example. You have the IO is lower than the VDD core in some case. There also another type IO called LVDS, stand for low voltage differential signaling. It's basically a pair of IO, and it's a switch at very low voltage between 0 to 0.5 volt. But the supply to the pad is actually at higher voltage, typically 1.8 volt. But the signal only switch between 0 to 0 volt to 0.3 volt. So those are two examples of the IO pad that have a lower voltage than the vehicle.
Very good. Thank you, Vũ. There's another question. At the core ring, is blue line ground below or above the red line VDD? Okay, that's a good question. So in here, it just represent the logical connections. So it doesn't mean this is a layer, right? This is just, hey, for VDD, we mark it red, but this is not the layout. So in practice, you will see they can be at the same level, a layer. For example, in your lab, you see the horizontal VDD will be in metal 9, ground will be in metal 9 on the top and on the bottom. And vertically, you have metal 8 on VDD and metal 8 on ground. So they don't have to be the layers have nothing to do with the logical representation here. So they can be on the same layers and depend on whether or not they go vertical or horizontal. So I guess you asked about above, below, you mean the layers, right? So okay. So keep the question coming. Very good points.
There's one more question of you.
Okay. Which metal for power routing? Is it isolated between power domain? Very good. So you see we typically use the highest metal simply because we want to have the low resistance. So when you go from the pads to distribute, sometimes you have billions, 20 billions of transistors in a chip. So you want you're gonna see the IR drop is very important, but as you know, IR, right? So the resistance, to minimize the IR drop, you want to have a lowest resistance. So low resistance means thicker metals and higher metals. So on the main trunk, then
This
you
meeting is
want.
being recorded.
Oh, you forgot to record.
My apologies. Thanks for the reminder.
Yeah, too much fun in Vietnam the last few days. You head out when?
I leave tomorrow morning. I'll be on a plane back to the States.
All right. Oh, okay. Have a good trip back. Okay, so to answer question. So you will use the highest level in this lab. You have an AP, right? A layer, and then you have metal 9, metal. I'm not sure if we have AP in the lab, but basically the highest layer and highest layer usually is thick layer. So typically you have an ultra thick, and then you have a thick, and then what you have regular. So usually the routing inside the chip are really the regular metals, and the lowest metal 1, usually is a thin metal. A lot of routing from metal 2 to metal 6, metal 8, whatever, are what we call regular metals. And then the higher level, you have a thicker one, you call thick metal, and then you have ultra thick metal, and you have the RDL redistribution layer, etc. So you want to use the as much as possible the higher layers first for RC, and then you will have to step down because metal 1 is used or metal 2 is used in center cells. So eventually you have to go all the way down to metal 1 or metal 2 to feed the standard cell with power. So you step up multiple grid before you go down. So the lower grid will be in the lower levels. But how about the size of VDD VSS usually is? Oh, another excellent question. You can see there will be a trade-off. So based on your power, we'll go over that. But based on the power analysis, you determine the width, right? Of course, if you want a higher, lower resistance, and you want to have wider wires. But if you do too big of a wire, too wide of a wire, then you take away the routing resources. So while you have good IR drop, but you have no more room to route the chip, or unless you grow the die, therefore you increase the cost. So there are trade-offs that require you to be accurate to have enough for the constraints and to meeting the IR drop constraint, but not too much just to impact your cost and routability. Wow, excellent question. Yeah.
Yeah, that's a really good question. I just want to add to that and feel that the side typically we would like to have the size of the VDD and VSS the same size at the IO pad. It make it easy to do the planning, and if needed, we can just add more pad, either more VDD and more VSS pads.
Yeah. So typically the highest layer is very thick, and you don't use them for routing purposes. Mainly, you use them to distribute the power. Yeah. Okay. All right. So going back to adding the ring. So we're talking about ring here, right? A ring means like VDD and VSS around a core block or macro block. You see this enclosed, right? It's a continuous loop. So you want to tell the tool to say, hey, what is the top layer and what is the bottom layer? This have something to do with the fact that if you have metal 9 and you go over some structure, you say, if you see a cross section connect all the way to metal 1, but you do a metal 4 here, then it will see a cross section of metal 1, it won't veer down. Right now maybe it doesn't make a lot of sense, but basically you have, when you have a route, you need to, when you intersect with another VDD underneath, then you want to veer down to make a connection. So this kind of control how deep you want to veer down. And then you want to have some veer controls by, say, by default, it will fill in the veers on all the overlaps, but sometimes you want to have less or more, and you can have these little control. So you set up all these control of what um, the ring looks like, the width, right? The pitch, the spacing in between them, and what layers on top and bottom, etc. You see more details on here that in later one. That really tell you exactly many different things that you can do to control the creation of this ring. Khánh Dương, is it possible if multi-voltage domains are routed on the same metal layers? Oh, absolutely, yes, as long as they are not shorted together. So yeah, they are different voltages, but they can be in the same layer, and as long as they don't touch each other, right? So creating a short. All right, very good. So now two types, block rings and core ring. Let's talk about core rings, right? So core ring, so you make sure that you don't select anything, and then by default it will build a ring around the core area. The core area you already defined, so it built outside of that core area. So in here you see this is called stack via top layer, metal 9 and metal 1. This is what I mentioned about controlling the veering down. If you have 4 here, then it won't veer down to metal 2, metal 3, metal 1 if the structure cross those layers. But in here we say, okay, veer, if you see metal 1, veer all the way down. So in here you say ring, right? Connect VDD and VSS net, right? And then layers, it said top, bottom, left, right, meaning what you going to be covered on the top, right? So the ring is around this, the ring is around the core, right? So what layers you want to use the top? In here you said 9 and metal 9 on the bottom, and then you say left and right on metal 8.
This meeting is being recorded.
Meaning this is all these blocks, right? Sometimes you say, hey, this block already have a ring, I don't want to build a ring around it. So you select all the blocks by using this select object command. And when you select, and then you do like before, you see all these, you set db to set all the attributes, how the ring is built, like layer, spacing, etc., similarly to the core. and then you use a command called that ring add rings, and I forgot to mention is the type called block ring. If you see over here, I forgot to mention this is the type core ring, right? So you have block ring and core ring. And then it will build for each macro. It will build a ring around it, similarly to the core, right? It's based from the macro. This is VDD, this VSS, and you can see the VDD and VSS. There's some smart sharing in between adjacent macros. But you use setDB to control the width, the spacing, etc. The VS. And then you type a command. You see over here, it select all these memories. And when you hit a command, it build all these string around it for you. Versus you have in the past, sometimes we have to do it manually by scripts. And then these type of rings, they put an attribute called block ring for future operations on these shapes. So that's a block ring, right? So that's pretty much for creation of the rings, and then the creation of stripes. Stripes are, like I said, it's straps. It's just lines, right? You see here, these are the rings. These are probably the IO rings, internal IO rings. In this test case, you already have internal rings, and then you build on the ring outside of it. It's kind of overkill, but anyway, so in addition to the rings around the macros, for the standard cell, you usually build what's called stripes or straps. So you will use a setDB command to add to specify what kind of things you want to do, or what kind of stripes you want to add, and then you run the command called add stripes, and you do a dash layer. So over here, for example, we will still say you do metal 9 to metal 1 for via stacking, and then you do a net, you do a layer. So in here you set direction horizontal. So you are building. So underneath here are standard cells. So you say, I want to build the stripes of metal 9 horizontally, and I'm going to do each of them with a 5. A spacing between them is 10. It doesn't mean, it doesn't say. This is a pair. So in between the two VD and VSS, spacing is 10, and set to set distance. Set means that this is a pair from here to the next set is 120, and then you start from the bottom here. So this is the core. So usually you start from the edge of the core and you start from the bottom. Means the first one will be offset 70 from the bottom. So this is how you do all these different numbers to specify exactly what you want to build. So this is horizontal metal 9, and then in addition you will build the vertical metal 8 in blue here, light blue here. So you still see add stripe, direction vertical, layer metal 8, and width, or whatever. So this is how you build the stripes. And these are the way you distribute the power to the standard cells. So the rings are the way to distribute power to the macros, right? And in a lot of times, we have we don't build rings, but we have power straps, like I mentioned, right? I show an example, and over here, right? A lot of time you have power straps like this, and then you run on top and you veer down on top of these pins. So you don't need a ring. So in some cases, to save areas, that's what you do. But it's really depend on your overall design. And I believe that is all I want to cover for today. And so in summary, you go through all the step to create the floor planning database in preparation for the placement step. But like I said there are more to power grid. We want to know what IR drops are, what EMs are, what kind of things we need to pay attention to, what kind of trade-offs we need to make in the creation of power grid. So we're going to cover them more on Friday. So look forward to more information that I prepared today. So we'll try to share with you as soon as we can. And then next week we'll be just wrapping up whatever else we need to cover for a complete floor plan. Before I hand over to But, who's going to cover the he's going to be teaching the placement and CTS. And last but not least, Tian will be teaching the routing step. So this is my last week. After this, I can go on vacation and relax. So yeah, we have 4 minutes before the break, or we can take a break now, or we can, if there's some question, we can ask now.
Sure, we had one question. We had one question come
Yeah.
in. After power
Okay.
planning, how do we check the assertions for potential violations?
So yeah, so I'm gonna cover that. I'm not sure what you mean by assertion, but we do have power grid analysis is the steps that we want to do to validate that the power grid doesn't have any EM violations, no maximum IR trough violations, no DRC, etc. There are steps that we need to make sure that we have high quality and clean floor plan before we actually do the placement. Yeah, we'll cover in terms of rules, the goals. So I do have a question. As I prepare for today, I have some information. Either I can go over the detailed technical now, or we can go over the labs and then go over technical detail later. Actually, it's better to go over the labs, not too much information in one section. So yeah, we'll go over a little bit more. Can you tell me exactly what assertion means in your question? Can or can, yeah. Or say yes if I did answer your question, so you don't have to.
So and Phil, let me add a little bit more. So at this
Power. Okay. Yeah.
Okay, yeah. So at this point, after floor planning, the only thing we're really concerned at this point is to make PG short free. So that's one of the check that we're gonna go over in placement. So
Awesome.
and
Awesome.
also the during the power analysis at RTL level, specifying the width and how much power grid. That is done, right? So you build a grid to your power specification, and then once you get to you place all the cells on everything, and then that's the
time it will be what we call analysis. However, we still can validate different things, and with the without the actual final circuitries, the methodology should be good enough for the tool to tell us that we are going to be good or not. And then if we in actual implementation, it could mean that we have to go back. So it's iteration process. If we might have to go back and do some fixing for power grid if your power turn out to be a lot more. So we'll go over that. Okay, so it's 5 o'clock, 10 o'clock. So let's take a 5-minute break, right, Dave? And then we can go back and do the cable need to drop. All right, we'll see you guys back in 5 minutes, and we can go over the labs. Hey, Bạc,